Recording, please. Okay, thank you.
Yes.
So, good morning, everyone, and welcome to CIRCMAN5 first webinar. Thank you all for joining us. So, the main purpose of today's session is to introduce the project and the pilot partners involved in the project and present the use case. So, each partner will basically briefly outline their role and focus area within the project, giving you an overview of how different aspects of circular and sustainable photovoltaic development are being addressed in CIRCMAN5. If we look at the agenda, so the agenda starts with a short introduction to the project by our project coordinator, and it will be followed by technical overview given by our technical coordinator. And then we will move on to the use case presentations from our partners in Spain, Italy, Germany, and Lithuania. And in the end, we'll have a Q&A session where you can engage directly with presenters, and we will be happy to answer your questions. So before we begin, we kindly request all participants to keep their microphones muted during the presentation so that the presenters are not disturbed by background noises and that everyone can follow the session clearly. So let's dive into the first presentation, Introduction to CIRCMAN5 by the project coordinator.
Good morning. I'm Haralambos Georgiadis. Unfortunately, Dr. Zaharaki have a delay with her flight, so I will present for SERF. Good morning, everyone. First of all, on behalf of the entire CIRCMAN5.0 consortium, it's a great pleasure to welcome you to our very first online webinar. I'm happy to open the session, which marks an important step in our shared effort to reshape the future of photovoltaic manufacturing through circular innovation and Industry 5.0 principles. Can we proceed to the next slide? Thank you. The energy transition and the decarbonization goals we all aim for cannot be achieved without rethinking how we design, produce, and manage photovoltaic systems across their entire life cycle. CIRCMAN5.0 is committed to building the technological and systematic foundations to support this transformation, not just in theory, but in practice. The scope of CIRCMAN is to deliver digitalization solutions for tackling the challenges in all the four phases, which are product design, production planning, manufacturing process, and end-of-life and recovery of the solar PV industry. At the core of the project lie 4 industrial use cases, each of which will be presented today. These pilot sites from Spain, Italy, Germany, and Lithuania showcase real-world applications of circular economy principles in the PV sector, tackling challenges such as sustainable by design product development, digital production planning, AI-driven decision support, and smart end-of-life strategies. Through these pilots, we aim to generate tangible outcomes such as tools, metrics, and digital platforms, scalable models that can be adapted by other manufacturers, and ultimately a roadmap for circular transition in clean tech industries. We are 90 partners in 8 countries, and the pilots will be described later. The next slide, please. Of the most important tools we have, it's the development of AI-based tools to support circular design and production. There is the creation of digital circularity registry for PV components, the integration of end-of-life planning into the manufacturing phase, the generation of scalable blueprints for circular transition in the PV sector, contribution to the EU policy alignment and standardization efforts that you may see is very important, and of course, promotion of skills, training, and industry awareness. The next slide, please. Thank you. As I said, our main purpose is to showcase how circular manufacturing strategies are being applied in real-world PV industry settings across Europe. We will present you the 4 industrial use cases. We highlight the challenges solution across the full PV life cycle. We'll demonstrate our tools and digital platforms and circular methods developed so far, and the foster collaboration among PV industry professionals that is very important between professionals, researchers, and policymakers. Today for this webinar, we expect a greater awareness of scalable and circular strategies, and the knowledge sharing between technical teams and industry stakeholders, and aiding for refining tools and approaches in the next project phases. Here today we will gain first-hand insight into these implementations, and I encourage you to engage actively during the Q&A session that follows. The next slide is for the next participant. Thank you for being here today. We can proceed with the rest of the other presenters. Thank you very much.
Thank you. So now we will go on to the technical overview by our technical coordinator, Soteris from ICCS.
Good morning. Good morning also from me. I'm Soteris Messinis from ICCS, the technical coordinator of this project. Passing through a technical overview of our project, we are focusing on design for circularity, optimizing photovoltaic panels production, and ensuring effective end-of-life recovery, as pre-mentioned by the coordinator. One more core principle of our project is also a human-centric approach using a co-definition, co-creation methodology with the parallel involvement of end-user stakeholders throughout the project. And now, as regards the technical architecture, in this figure, we can see the layered architecture of the CIRCMAN framework, which is designed to support circularity. In the highest level, the CIRCMAN solution features a cognitive digital twin-driven decision-making system that provides key functionalities through a CDT-driven decision support system and an AI-based recommendation engine that are used to optimize material utilization and, of course, guide end-of-life strategies. This solution is expanded further into two distinct layers: the environmental impact assessment layer, that includes models for embodied energy and carbon assessment, AI-based algorithms for distribution routing optimization, the corresponding AI-driven forecasting of environmental KPIs, and the circularity and life cycle assessment framework. The simulation and modeling layer incorporates AI-driven parametric techniques to support a good design, and a machine learning engine for the enhancement of production planning and the potential defect detection during this the production. In the middle level, the architecture also includes an ontological production information modeling layer, which establishes semantic interoperability for data from diverse sources, and is implemented through the manufacturing and product user data using AI asset administration cell protocols. And this happens in order to have the data management at the core of our project in parallel with the rest of the tools. So in the same level, we highlight in the right part of this figure the CIRCMAN5 cross-cutting solutions, which include the cognitive digital twin, the digital product passport platform, and the collaborative space. This will facilitate the exchange, the circularity of PV knowledge, exchange of this knowledge and data, and is supported by a web API that incorporates specific standards, and a blockchain information service that is used to ensure data integrity and interoperability throughout the project. Finally, the architecture is grounded in the CIRCMAN5 application layer, which illustrates the application of the framework across the 4 different photovoltaic lifecycle phases: product design, production planning, manufacturing processes, and the end-of-life recovery. And on this layer showcases 4 pilots that are led by our partners ONYX, SUNAGE, ASCA, and Solitech. And before giving the floor to them, let's briefly mention in the following 2 slides the key challenges in circular manufacturing of PV panels. In general, and summarizing all this technical information, CIRCMAN addresses the hurdle of integrating diverse data from design to production by using standardized asset administration cell protocols and semantic modeling. It overcomes the limitations of traditional life cycle assessment with the development of dynamic life cycle assessment model powered by AI to accurately predict and optimize the environmental footprint. In the following and in the next slide, we can see the rest 3. It simplifies the complexities of circular production planning, like handling recycled materials, through machine learning assisted optimization for resource allocation, It ensures transparency and traceability using a digital product passport based on the distributed ledger technology. And finally, it ensures scalability and adaptability of its solutions to the cognitive digital twin. Our advanced AI models, the digital product passport, allowing them to evolve across the wider photovoltaic industry. And that's all from my side. We can go on with the use cases description. Thank you very much.
Thank you, Soteris. Now we will move on to our pilot partners. So the first presentation will be by ONYX from Ismail.
Hello.
Ismail?
Yeah, can you hear me?
Yes, we can hear you.
Okay. So, hello everyone. My name is Ismail. I come from ONYX. We are one of the pilots. We are placed in Spain, and we are the pilot which is more focused on the part of the product design. And first of all, I'm going to introduce ourselves a bit, and then I'm going to move to the use case that has been planned in the last months inside the CIRCMAN project for our pilot. So as I said, we are placed in Spain. We are a BIPV manufacturer. And what characterizes us the most is that we try to sell that our product is not just something for generating energy, but it's a construction material. And we try to adapt ourselves as much as possible to every project. And in order to do so, we have a wide set of different customization items, such as color for our products, such as different thicknesses, different coatings, different sizes, and all that. And because of this, we need to explore constantly new materials, new possibilities, and this is the point to be tackled inside this project also. So next slide, please. This is a brief description of our manufacturing process, which I'm not gonna go too much in detail, but essentially we could differentiate 8 steps. First of all, we acquire all the raw materials. Now we have many of them inside our production line. We have different types of cells. We have different types of glasses, of encapsulants. But regardless of that, we are always looking for new ones to be tested and to be implemented under the manufacturing process. Then we have the welding of the strings, which is done with one of our machines here in the factory. And once all the cells have been welded and the strings have been made, we make the layup of the modules and a first electroluminescence to check that all the cells are in good place and none of them is broken. Then we interconnect all those strings and we proceed to laminate the panel. And once it goes out of the laminator, we place the junction box so that the current can flow out of the module. And we proceed with the quality control of our modules. There on point number 7, I wrote flash test, but also some visual inspection is performed under the modules. Yeah, and finally we have the packaging that is added as another extra point of the manufacturing process, as it also has to be taken into account for circularity items, for example. Having said this, I will go point by point to all the tools that in the last few months were concerned to be tried, to be implemented, and under the CIRCMAN project. First of all, we would have an AI-driven parametric eco-design technique, which, as we intend to implement it, is somehow giving the AI an inventory of all the parameters that can be considered in order to design our modules, and making it help us to better design each module for each demo, each project, taking into consideration all the necessities of it and also the environment in which the module will be placed and so on. Next slide, please. Then we would have the lifecycle assessment. Right now, in ONYX, we have a global EPD for a family set of our products, like 3 or 4 different types of modules. but we would like to perform a life cycle assessment of different modules with different configurations, and also trying to compare them, to compare these results with those obtained for a similar module manufactured with different or new materials. This is trying to manufacture a pretty similar module to one that we may produce now, but using new materials and somehow checking if the new one gives us better results, not only in terms of power, but also in terms of environmental footprint and so on. Next slide, please. Then we will have an AI-based analytics for material comparisons, which essentially we expect having somehow a database in which we can compare some environmental and circular analytics of the currently used materials we have now, and be able to compare them with this same data for new materials, which will be in the future implemented or not, but at least compared and having the possibility to compare both scenarios. Next slide, please. Then we will have the digital product passport, which would be something not thought only for us, but also for the final customer, which would be pretty useful, because essentially it would be like, well, as the name says, as a passport of the product, which enables the final customer to check what was the environmental footprint of the product, not only coming from the raw materials, but also coming from the manufacturing process to whom it was performed. Next slide, please. Then we would have the machine learning assisted production planning tools. This is thought to be implemented under the manufacturing process. Also talking again about those new materials. Implementing new materials not only changes the final aspect or the final items of the product, but also changes the way in which it will be manufactured. Maybe some of the points of our manufacturing process that I explained at the beginning would be subject to some changes, maybe in time of lamination or maybe in time of welding because of the prestations of the materials. So in order to see how this could change, the machine learning assisted production planning tool could be pretty useful for us. Next slide, please. And something similar, but in a bigger scale, would be the cognitive digital twin. Cognitive digital twin would be software that simulates our production planning the whole way around. And if this is aligned with the previous mentioned tool, we could see how changes in one of the steps would affect the overall production planning. And in order to do so, we need that digital twin that replicates our manufacturing process and that is able to make changes in one of the steps if needed regarding the previously mentioned tool. Next slide, please. And finally, we have the AI-powered defect detection, which is built in a parallel line to all the previous mentioned one, as all the previous mentioned one were more focused onto the design and the manufacturing process, using our materials and using new materials. This one tackles the end of the manufacturing process before being sent to the final customer, which is the quality control. Right now, as I said at the beginning, we divided it into two steps. We have the visual inspection, and then we have the flash test and the electroluminescence to see if any cell is broken, or to see if there is any mistake on any part of the module. All this could be optimized by using AI techniques that somehow detect those defects without the need of someone being all the time revising. And that's why I say this would be in a parallel line. And yeah, these are all of the tools. So a bit on summary. I made all these points in here, but what I want to say is that we are really grateful to be part in the CIRCMAN project, and we expect to be somehow improving our production line, either by introducing new materials or even if in the end it's not possible to introduce those materials, being able to checking how they would affect into our production planning, and maybe not now, but in the future will be possible. Yeah, as I said, also that parallel line of the quality control, if in the end we are able to introduce it in our production process, would be very helpful and yeah, very time saving for us. So this is all from my side. I give the floor to the next pilot. Thank you very much.
Thank you, Ismail. So now we go on to our next pilot, SUNAGE, and our presenter is Alex.
Hello, everyone. Can you hear me?
Yes.
Okay, perfect. Hello, everyone. I am Alex Ferrario from SUNAGE, and I'm going to introduce the second pilot partner of this process, that it's of this project, that it's SUNAGE. Okay, you can go on with the slide, please. We are SUNAGE. We are a PV manufacturer from Switzerland. We are located in Balerna, Canton Ticino, and we have over 15 years of history in PV modules production. We started 15 years ago with the classic PV modules, and then we move on with different products, focusing on colored PV modules. Again, we are our company is SUNAGE, and we developed our product that is focusing on the coloring. That is its name. It's SUNCOL. Okay, we can go on. As I was saying, we born in 2007, and we started developing classic PV modules for roof integration. Those were quite standard modules, so for application on roofs, they were made with glass backsheet modules with classic frame. Then in 2015, we moved on and we started producing colored PV modules. The logic was always the same. They were BIPV modules, so for application, always for roofs. They were made glass backsheet or glass modules with a frame that they have to be mounted on roofs and on structures. Then on 2017, we finally moved into the production that we are carrying out also nowadays, that it's focused on the BIPV, so photovoltaics for integration in buildings as facades or roofs. But the PV module, it's no more something to be applied on the substructure, but it's itself a construction material, so that can replace the classic finishing of buildings like glasses or other type of plastic that it's used to cover the buildings. And from 2017, we moved on this topic that it's nowadays more than 90% of our business. It's focused on these modules, these colored PV modules. Okay, we can go on. As I was saying, the main change it's that we went from classic application of PV modules to integration of these components that can actually replace in these images. You can see that instead of classic tiles, you can see the PV modules that have been installed in the roofs. They can ensure waterproofness of the roofs by creating active energy. So this process together on the roofs, but also on the facades, it's exploiting some surfaces that weren't used before, and give us the opportunity to produce energy that in another case these surfaces won't be used at all. Okay, we can go on. Here in SUNAGE, we are focusing on the high customization of our products. As you can see in the images reported here, you can see that we have a lot of different colors available. We have a darker color like blue, browns, greens, and so on, but we have also a lot of light colors like light grays and white. And we have really high efficiency coming from these colors. We have also different options that are made with digital printing technique that we can replicate patterns like stones or different materials currently used to cover the facades of buildings. In addition to this option, we have also the possibility to select the glass type. We usually use the flat satin finish, that it's the one that's most used in the sector, but we can also have shining glasses or structured glasses that can ensure a completely different aesthetics of the module, guaranteeing trying to satisfy all the needs coming from the industry. So architects can ask their needs, and we can almost satisfy everything they want. Okay, we can go on. These are just a few projects that we made in the last years. As you can see on the image on the right, the building is entirely made of PV modules, both on the roofs and on the facades. This building, it's an active building, so that it produces more energy than it uses. And it's a really dark color, and so also the energy production coming from these modules, it's really high. While on the left, on the upper side, we have other two buildings that are made of a reddish color. It's two villas here in Switzerland with a particular fixing system. And on the bottom side, we have another project that it's for a university here in Lugano, where the PV modules are the white strips. It's more than 3 meters long white strips that are following the sun. They are used also as to create shadows, because inside this room there is a conference room, and so according to the user needs, they can follow the sun and can create shadows or in something in the middle in order to create correct lighting of the room. Okay, we can go on. So up to now, I presented more or less SUNAGE as a PV manufacturer with projects and what is our identity. Here we can move in the process that we aim to follow inside the CIRCMAN project. In the upper part of the slide, you can see the processes that are currently done here in SUNAGE. So there is the first one, that is the administrative workflow, and the second one, that is the production process. As Ismail have presented, our production process is quite similar. That it consists in the cleaning of the glasses, stringing of the cells, assembly of the panel, lamination, and then in the application of the junction boxes, cutting, and in the final testing. We have here in SUNAGE, we have really important focus on the testing. We perform 3 EL detection stages in order to check the healthiness of the cells in all the process, in order to ensure a really good product as once it's packed. And our process relies in a lot of different machines. If we can move on the next image, we can see the summary of the machines that are used in SUNAGE manufacturing process. We have the stringer and the laminator that are the one on the left side. that are the most important machine, because the first one is the one that it's stringing the PV cells once with the other, and it's creating the PV circuits, while the other one, the laminator, it's the second in order of importance, because it's the one that it's creating the PV modules. So it laminates the two glasses together in order to create the final product. Then we have all the robots, conveyor belts for transportation of the products, and on the right side we have the testing machinery, that is the solar simulator and the electroluminescence camera that provides all the measures, all the testing equipment for the modules, in order to be sure that both from the mechanical point of view everything is okay, and also regarding the energy production, that it's consistent with the nominal values. Then we can go on, please. Here there is a visualization of the PV module that is produced here in SUNAGE. Here we produce mainly glass PV modules, so that we have a front glass and a back glass. The thickness of the glasses can be different according to customer needs. And then there are the encapsulation layers. Usually they are made of EVA, that it's a special material commonly used in the solar manufacturing sector. And then inside the sandwich there are the PV cells that are the one that stringed together are providing the energy production of the modules. At the end, we can keep also the fixing system of the modules. We can provide fixing system both for roofs and for facades, or we can apply the frames as actual as classic PV modules. And then we have the packaging that is made with cardboard. Okay, we can go on. Here there are the summary of the outcome that we hope to retrieve to follow inside the CIRCMAN 5.0 project. As Ismail have already presented, almost all of them are common between the two companies, but we wanted to focus mainly on obtaining some different materials, some different raw materials capable to reduce the environmental footprint of the manufacturing process. Together with this scope, so in finding different materials, we also wanted to find some alternatives, so some different suppliers that can provide us with all the raw materials needed for the PV modules production that are closer to SUNAGE, in order to reduce the environmental footprint also for the transportation. We want also to develop the cognitive digital twin of our manufacturing site, in order to have a simulation of the manufacturing process, identifying bottlenecks, and developing different strategies capable to reduce the CO2 emission of the process. We will also carry on an LCA studies for different families, because also SUNAGE have already developed an APD for certain families of products. And here in the CIRCMAN framework, we want to enlarge these families, and we want to check if with the different strategies that we will develop, we can also obtain better values following the directory coming from the APD. So this is it, and thank you all for your time, and I'm leaving the floor to the next presenter.
Thank you, Alex. So now we will move on to our third pilot, which is ASCA, and presenter is Pavel.
Hello, this is Pavel from ASCA. Next slide, please. I'm presenting our company, which is a pilot use case of CIRCMAN dealing with organic photovoltaics. Organic means in this respect not made of plants, but made of plastics. So it's plastic solar modules we are producing, giving the opportunity to be to have flexible solar modules. They are colored in red, green, blue, transparent, and can be made in different shapes. The speciality, one speciality is they are made by printing. What you see on this photo is a relatively small printing line where we can do the roll-to-roll coating and printing of these flexible PV films. Due to the printing, the environmental impact is already relatively low, as it's all low temperature processes involved in the manufacturing of the materials. But nevertheless, we try and aim in the CIRCMAN project to be even more effective. Next slide, please. Few words to our background. Our mother company is Heringbau. It's a German construction company, so mainly dealing with concrete, but it's also it's special design concrete, so making nice, beautiful facades and other specialities, construction materials. So this is we are a subsidiary of Hering, and based in Germany, close to Würzburg or close to a bit far, but close to Frankfurt, just to have an idea where we are. Next slide, please. OPV, organic photovoltaics, as I said, has the benefit of being flexible, transparent, colored, and we have a freedom also in the shape. On this picture on the right, you see an example of such a module. The shape of the module is trapezoidal. You can look through the module. You see the clouds behind. You see the whatever object through the module. You can see besides the shape, we can also implement holes or indentations on the rim. Due to the flexibility, due to the plastic substrates, the modules are also relatively lightweight, being able to made on facades or on lightweight structures on the outer building of the buildings. So all this together is enabling us to have energy surfaces on parts of buildings where it seems impossible or very difficult to do with classical PV. Next slide, please. These modules you've seen in the previous slide were manufactured for an building of Novartis in Basel, Switzerland. You see on this facade, it's a media facade. There are more than 10,000 of these modules integrated into this facade. The holes you have seen in the previous slide inside the modules are equipped with LEDs. So the outer facade of the building can show text, images, videos, and so on in either all colors for the LEDs, and it's powered by the facade itself. So it's a self-powered media facade. Next slide, please. Another example where it's not obvious that it's photovoltaics at all. It looks more like a piece of art, an image. Is from the Dutch pavilion of the World Expo in 2020 in Dubai. So it's you don't realize that it's technique. It just looks like an integral part of the installation of the facade of the building. Next slide, please. Here's an overview on on this variety we can produce. So it can be round, it can be rectangle, it can be trapezoidal. In the upper right, you see in the form of a flower, of a lotus flower. Below, it's like a banana leaf, or you have more technical, like this trapezoidal, or the bottom right, where we have some holes or kinks in the module, depending on the need, on the requirement of the customer. Next slide, please. Very brief overview on our capabilities. As I said, we are doing coating and printing of the modules. So therefore, with relatively small equipment, we can produce already up to 100,000 square meters of PV material. There are different other like lasers for the interconnection, screen printers, CO2 lasers to cut out the pieces. We have an encapsulation line, as we need different shapes. Besides CO2 lasers, also CNC milling if it's larger material. And of course, injection molding for contacts, sun tester, climate chamber, and all this stuff. Next slide, please. Very roughly, we structure our production of our product into two steps. The first is the OPV film. This is what you have seen 2 slides before. These different colored and shaped films. Here we start with an roll-to-roll slot die coating and roll-to-roll laser rings and screen printing and so on. End up with encapsulated films, which are then also cut out by lasering. Next slide, please. These films are then assembled towards a product, which are more the classical panels of something like from ranging from a quarter of a square meter up to several square meters. So here we assemble multiple of these smaller modules towards a panel, have bypass diodes, making also what's otherwise called stringing, do the lamination, which is done externally at the moment, make contact application, eventually milling, and that's it. Next slide, please. The link to the CIRCMAN is so on each and any of these intermediate production steps. We could do some improvement. So therefore, we developed in the CIRCMAN project use case scenario for ASCA, which I see roughly is 4 blocks. The first block is all dealing with the materials themselves. So having an IE-driven eco-design tools to evaluate alternative materials for the OPVs. And this together in conjunction also with the life cycle assessment to see what are benefit or drawback of some material options or the interaction between the materials. And also on the performance and stability themselves, it's usually throughout testing, so quite long lasting. And if IE-driven simulation tools could eventually help here. The second part is to integrate the IE to improve the layouting. So when we have these different shapes and the boundary condition of the customer, like where should be the contacts, where should be holes, what is the required voltage, and so on. We have already some semi-automation here using a software, but it's still quite some interaction with the users and quite some know-how here. So if IE could help to improve this and mainly to speed it up and to test more alternatives to get not just 1 or 2, but maybe multiple options to compare them in terms of material usage, waste, error tolerance, and so on. The third block in this use case scenario is around the production and the manufacturing. So to have a better planning tool for the production, optimize the manufacturing using a cognitive digital twin, and also to optimize the different production steps with each other. And the fourth block of this use case scenario is about the defect detection. So to detect errors, defects as soon as possible, or even before they even occur. So have the feedback of the machines and some pattern recognition, and see, okay, most probably something is going wrong and will end up in a defect if we don't do counter actions and do these counter actions before these defects occur. Next slide, please. So for us, the main objectives, and I see this slide as in somehow a translation of the more of the previous slide towards the language we as a manufacturer understand better, and like we want to have in process optimization, so lower material usage, less energy consumption, and so on. We would like to have a higher degree of automation with the outcomes of the CIRCMAN project. We would have a better optimization of the product planning, that this is done much more effectively. We would like to have new and or improved quality control measures and procedures, and finally also to have the digitalization through the digital twins. Next slide, please. So finally, the outcome is it should, even though we start with an quite good eco impact as it's all printing and no high temperature process is involved here, we would still be better in terms of environmental footprint, reduction of CO2 emissions. And of course, if we see something like increase the resource efficiency of materials, it also means to be lower in costs. If we don't have waste and less rejects, it's better cost effectiveness. Also, to reduce the energy consumption is would be really cool, and to be more effective with workflow and use of labor and so on. Also on the materials themselves, would be really a benefit from the CIRCMAN project, even though it could be here that for at least for some materials it's difficult, as we have quite special chemistry involved here. There are not much a huge amount of materials outside, so the learning for the pattern recognition may be difficult, but for another part of the materials, this can be quite useful, as it's standard materials like also the EVA or stuff like this. So I think that's it from my side. I'm happy to go into the question answer later, but now I give the floor to the fourth pilot. Thanks.
Thank you, Paul. So now we move on to our next pilot, Solitech, and presenter is Tejas. Are you with us?
Yeah, thank you, Pavel and Nadia. I will present the fourth one, the last pilot. So I am Tadas Adavičius. I am from Solitech. We are located in Lithuania, and we are a PV module manufacturer. Next slide. Some facts about the company. So we have a quite small production line, 250 megawatts. As a company group, we are also manufacturing other products. One of them is progressive E-lenses and battery systems. So a bit similarity is that all these products are multi-layered, requires a lot of engineering. So we have this competences as a company group. The building is operated by renewable energy. It's a family business, and we've been in PV module production segment for about 10 years. Originally, we started from solar cells production, but in Europe, it's quite difficult to produce them. Next slide. The main difference between other pilots is that we are more a standard production process. We are not going customized. We are going more or less standard. We are producing durable glass models for different applications, roof integrated, solar roof, or agro PV, or PV models for alpine that requires quite a lot of durability. Next slide. We are focusing on integrated solution. It's carport PV. We have our own utility scale systems where we test with the models with trackers with increased bifaciality, agro PV, and latest developments. We have a couple of pilots, PV models as a noise barriers in highway and railroads application. Next slide. This is our production steps. We differentiate it before lamination and after lamination. So it's quite a standard approach from stringing to loading each component on top, laminating, and then testing. We also have troubleshooting in case the malfunction, wrong soldering. We are able to have a repair of the cells before the lamination, because after lamination you cannot open the cells. Next slide. In this project, we are aiming to adapt the innovations for 4 products. One of them is commercial glass. Second one is prototype a tandem model, which is the next generation models that use 2 types of cell technologies, a PVT model to generate electricity and heating, and a concept of encapsulation-free PV models. Next slide. What we expect from CIRCMAN is to have a higher recycled content by having capability to choose suppliers, to check if the performance will not decrease, such as in the glass. If you have higher recycled content, you might lose transmittance of light, which will affect efficiency. We want to have a capability to verify sustainability claims from suppliers, LCA calculations, alternative materials, EPD calculation. And what's the main difference between other pilots is that we also want to go into end of life, and mainly the reuse. So we want to analyze 2 cases. So one is that after removing the model from old PV plant, can you identify if the model is still has some life? So can you be sure that if you test the model, an old model, can you be sure that you can sell it and it will last for 2, 5, or 10 years? Another case is analyzing through inverter data existing PV plants, so that before dismantling, you could make decision which PV models or strings is still in good health, so you can reduce testing costs and sort the good models versus bad models already in the field where the PV system is installed. Next slide. Yeah, so when it comes to end of life, we want to determine on electroelements, IV test, if the PV model is still healthy, how to do it, and determine if models in PV field are still reusable based on aging patterns. So we have this capability since we have our own utility scale parks, we have the data, so we will test if we can determine from inverter data if the models are still, if we can forecast, if we can see that comparing with the original testing results when the PV model was manufactured versus after 5 years, we can make correlation and see is the degradation is as it's supposed to be. If not, we can make a decision that this model will probably not be fitting for second life application. Yes, next slide. Yeah, that would be all about the Solitech case.
Thank you, Lalas. Thank you to all the presenters for nice presentations. As now we have all the presentations. Now we move on to the Q&A session. So anybody in the participants, if you have any questions, you can now ask.
Hello, I'm Babis Rizadis. I have the raised hand. Can I
Yeah.
ask something? Let's say for the latest presentation, regarding the decision that you can take in order to determine which it's reusable or not, can actually AI to help something like that? And also, if we assume that the PV has more or less typical usage, not something extreme, let's say, on extreme weather conditions, maybe, or something that conflicts regarding his life age. Will be the digital passport platform could help if you have all the data regarding this, the specifications of the PV, and will reflect the decision even before you see it. There are maybe, for example, more possibilities to use it, judging from the history of the cycle.
Yes, theoretically. So if you have a history of PV model with batteries, you can store easily the performance data. But PV models, it's a bit difficult. But what you could do is, if you have bill of materials, type of encapsulant or backsheet is used. The recycling reuse companies, some of them, they collect this data, the reason of failure of one or another model. And if you note that one type of encapsulation has higher failure rate, this is one of the decision to help to know if my model that has the same encapsulation, it probably will not be fitting for a use. No? So you can make some, you can integrate it in decision making.
Perfect. Thank you.
Thank you. Any more questions?
Maybe could ask in order to help the conversation. Again, to the other participants. I would like to know during the designing phase of PV, because we saw some very interesting shapes that you can build. Is something that is unlimited? You can create, design any shape of PV, for example. If yes, how AI could help on this? For example, as the one partner said, the AI-driven simulation models needs to predict the performance and the stability. Can't a shape change the performance, may say, of the PV, and an AI can predict how will perform later on? For example, I'm not quite sure, but if you have unlimited shapes that you can build, somehow they manage to change the performance of the PV, of the same PV material with different shapes, and AI is something that can help with to define and to suggest to the client, maybe to the customer, what to use.
This is Pavel. I'm not sure if I get it fully. So we have design is for us two things, more or less. One is really the how to say, the physical shape, yeah, like if it's a leaf or looking like I don't know, a football like a banana leaf, trapezoidal shape, whatever. And here, for these shapes, there are usually different other boundary conditions by the customer, like he needs the contacts at a specific position, he needs a special voltage, and so on. And this we are doing with an layouting software and some manual input on how to distribute the cells that we have, that we fulfill these boundary conditions to 100% or as good as possible. Here, we have relatively simple approaches on how to do this, but nevertheless, the decision space is nearly, maybe not infinite, but very large. So here, I think that IE can help to make suggestions or to test different things on what to do. So this more the physical, yeah. The other part is the design and the, how to say, of the stack on which materials are we using. We of course, if we have a different color, we are using a different absorber material. So it's a different chemistry we're having here, and different chemistry means it is different, whatever energy levels can be more prone to oxidation and therefore to degradation, but or on the other hand being more effective in the power conversion and so on. This is usually huge academic work and quite some testing and production of materials. So this was the part where I'm not sure if IE can really help in finding better materials, as this is very special and going into the direction of I don't know, molecular design and interaction with whatever the environment.
Maybe,
yeah, please.
maybe I can add, Tadas from Solitech. Just an idea that if you look at the components level, one of the issues in the industry is the costs are decreasing so much, manufacturers are decreasing thickness of the glass. And you have two variables. Let's say you have glass thickness, and you have how it's installed, and a hill crush increase in probability in different regions. You know? So maybe it would make sense to make a model and to so that some countries in procurement process, they would take that into consideration, that increasing hill crush will have impact. And then you can model the design of PV model, what's the thickness, maybe the cables, junction box, silicon amount. This can also be improved in decision making.
So in a practical way, let's say that you take an order from a potential customer that he would like to add some PVs on here stage building, let's say. How you believe that CIRCMAN could help with the tools, even with decision support system, and considering that you know better what the customer asks for and his demands, and maybe when you have to later suggest him that it will be better for him to use, for example, with this shape, etc. How CIRCMAN could help on this decision, for example, to provide data from the historical data from a similar building, let's say. That is something that would help in order to make a better decision and almost automatically decision about how to implement the solution that you will better later suggest to the customer.
Maybe one of the ideas I think most of the innovation relates to designing the product or having access to information, and the benefits will be felt, will be longer lifetime of PV model or reduced recyclability costs. So these type of clients are the big utility scale systems that attract funding from big investors, pension funds, and so on. They calculate all lifetime of the project, including recycling. So these are maybe the clients that would consider investing so that they could reduce the overall project cost and in very long period. So that's one option, I think.
Yes, thank you.
Thank you. So if there are no more questions, I think we can close the session. Okay. Thank you so much, the presenters who delivered such a nice presentation and provided a deep down overview of the project. And also to the project coordinator and the technical coordinator for providing an overview of overall project. Thank you all, and thank you all for joining us. Have a good day. Bye-bye.
Thank you all.
Bye.
Bye.
Thank you.
Thank you all. Have a nice day.
Bye.
Bye bye.
Bye. Thank you.
Bye. Bye bye, everybody. Bye.
Bye. Bye.